This lecture we study the capacitor filter and derive the expression for the ripple factor. So already in the last lecture we studied how the capacitor blocks DC and allows AC. Now here this is the signal applied full wave rectifier input output signal actually that we are applying to the as an input to the filter. If we connect the capacitor in parallel with the resistor, then that is called the simple shunt capacitor filter or capacitor filter. Now here, when this signal is, now here let me draw the diagram. So this is the rectifier circuit. Both cathodes are shorted and the capacitor is connected like this, and in parallel load resistor RL and C. So now when the diode is conducting, when suppose for example diode D1 is conducting, now this is because of the D1 and this is because of the D2. D1 is conducting, so current is available at the output, diode conducting and output. So because current is coming, so capacitor will charge it. Whenever there is a current enters into the capacitor, capacitor charges. If current is not available, current is not there, then the capacitor will try to check the path to discharge. It will discharge the capacitor will try to discharge. Now, when the diode is conducting, here, this is the signal at the output. So capacitor try to charge. It will charge up to the maximum. When the capacitor is connected and it is charging up to the maximum, then here the diode at the input also. Now, if you see, this is the input signal and this is the output signal. So when it is at the input, it is reaching to the Vmax. At the time, it is reaching at the output also, we reach into the Vmax. So now here it is the Vmax and output is also Vmax and the capacitor charged up to the Vmax. But when the input is falling, reducing, that time without the filter, so output is also following the input. But now with the capacitor filter, now capacitor is charged to the maximum and it will stay at that maximum position. So now at the input, if it is voltage is reducing, it is falling, that time capacitor output voltage, capacitor charge will not fall immediately. Now here it will, the voltage is V maximum. So what is forward bias? Forward bias means, now just we have studied that if we apply the positive to the positive terminal, positive material and negative terminal to the negative material, then it is a forward bias. Diode will conduct this. We studied in the PN junction diode. This is the basic definition. Actual definition is, so irrespective of the voltage, now here the anode voltage should be greater than the cathode voltage. How much greater? Plus cut-in voltage time. Now if I am applying V voltage over here and here also V voltage is there. If both the voltages are equal, then the diode will not conduct. So if the anode voltage is V plus 0.7, for silicon I am talking, so 0.7, then we can say that diode is in forward bias and it will conduct. So whatever the supply you will apply for the negative or positive, irrespective of the supply. Now here we need to check that anode voltage should be greater than the cathode voltage. Then only we can say that diode is conducting. Now here with the filter, now if it is charging up to the maximum and it is acting like a battery, and here the cathode voltage is up to, it is maximum. When it reaches to the maximum, both anode voltage and cathode voltage, both are at the same voltages, then the diode will not conduct. Why? Because the potential difference must be cut-in voltage. Now, V plus 0.7 minus V is equal to what? 0.7. This is should be is equal to or greater than or is equal to 0.7. So then only diode will conduct. Now here if both are Vmax and Vmax, diode will not conduct. Thereby no current is available at the output. So thereby what? The capacitor will not charge. If current is coming, then the capacitor will try to charge. If there is no current, then capacitor will try to discharge. When the diode is not conducting, then only the capacitor will check the path. Now here the resistor is available, so capacitor will discharge through the RL. Now here you can see after reaching the maximum, diode is not conducting, thereby it is discharging. Now here the capacitor is discharging, and here if you see for the second half cycle, the voltage is increasing. So thereby what? Again, the anode voltage is greater than the cathode voltage. Where the anode voltage is greater than the cathode voltage, again diode starts conducting. So if the diode starts conducting means what? Current is available at the output. Thereby what? Again the capacitor will try to charge. Now here capacitor discharges like this. And for the next half cycle, again capacitor charges. It reaches to the maximum and it repeats again. Now, when it reaches to the maximum, diode will not conduct again. No current is available. Capacitor will discharge. Like this, now because of the charging and discharging, almost the output waveform look like a DC signal. So DC signal means what? Pure straight line. But here it is coming like a now charging and discharging. Still, it is not a pure DC. Some ripple is available. Now here I'm showing the pure AC component as a VR peak to peak. Some ripple, R indicates what? A ripple, peak to peak. Peak to peak VR, it is not RMS value, peak to peak. So this much ripple is available. So what is the ripple factor for the capacitor filter that we are going to derive now? And here, if it is discharges slowly like this, then almost it is looking like a DC. Now, if discharges slowly, then it will look like a straight line. So, how the capacitor will discharge slowly? As the capacitor value, by increasing the capacitor value, or by increasing the resistor value, or by increasing both the values, we can achieve the pure DC. So, means what? Ripple factor is reduced by increasing the R and C values that we are going to derive. Now here if you see, this is T2 is the discharging, discharging time, and T1 is the charging time. So total time is equal to, now here from here to peak, it is nothing but what? T by 2. This is the input in this case input. The total time is T. If I say time period is T, now in the full wave rectifier, time period is what? T by 2. So T by 2 is the time period, and this T by 2 is equal to what? T1 plus T2 is nothing but what? Charging time plus discharging time. Or T by 2 is equal to, you can also write it as a T2 plus T1. Now here if you see, T2 is greater than the T1. If the discharging time is more, by increasing the capacitor and resistor value, so discharging time increases, and if more higher the capacitor value, then almost here if you see, the total time period is nothing but what? Discharging time only. So because the T2 is greater than T1, so we can write it as T by 2 is equal to T2. Okay, this we will use in the derivation. So now here we can see capacitor charge Q is equal to what can we write? V into C. And also Q is equal to, we can write it as a I into T. So these formulas we are using here. Capacitor charge is equal to VR peak to peak. What capacitor is charging? Capacitor is charging this much only, right? This is the capacitor charge. This we are representing what? Ripple peak to peak. So VR peak to peak into C. And it is how much charge it is, how much it is discharging, means what? IDC, it is discharging the current. Now, when no current is coming, the capacitor is discharging through the RL. Discharging means what? Current is flowing through the RL. Where it is coming? We're coming from the capacitor. So, what is the formula for the discharge? IDC into T2. Now, in the T2 time is for the discharging time. From here to here, charging and charging means what? How much it is discharged, that much it is charged. Why? Because every time it is reaching to the peak. Here it is reached to the peak. It is discharged, again reaching to the peak, again discharging means what? How much it is discharging, only that much it is charging. So here we can equate these two, thereby we can get VR peak to peak into C is equal to IDC into T2. Now what we have taken T2 is equal to what we said. Now where T2 is equal to T by 2 is equal to T2. So why we said that? So T by 2 is equal to T2 plus T1, where T2 is much greater than T1. So that's why we got T by 2 is equal to T2. Again, what is T? T is equal to reciprocal of the frequency. So what can we write now? This VR peak to peak is equal to VR peak to peak is equal to C. I'm sending to this side. IDC by C into now 2. Here I'm writing T. This also again I can write it as VR peak to peak is equal to this T. I'm writing in terms of frequency. IDC divided by 2FC. Now this is the ripple VR peak to peak. Now if you see, capacitor is charging like this and discharging, charging like this and discharging. And if you see, this is almost looking like a triangle waveform. This is looking like a triangle waveform. Now this I denoted it as a VR peak to peak. Now this peak to need to convert into RMS, VR RMS. So for deriving the expression for the triangle waveform, it is VR peak to peak divided by the 2√3. Like sine wave, we have derived the VRMS is equal to what we got? Vm by √2 we got, right? And VRMS is equal to, we can also write it as 2V peak to peak by √2. Here Vm is nothing but what? One peak. If you wanted to take 2 peak, this is nothing but what? V peak to peak is equal to 2 times. Now here you can write divided by 2. Sorry, divided by 2. V peak to peak divided by 2√2 is 2√2. So V peak to peak from this point to this point is equal to, we can write as 2 into V peak. So this is the RMS for the sine wave that we have already derived in the full wave rectifiers. Similarly, if you derive the RMS value for the triangle, now this is the expression. So this now we are going to substitute in this. So VR RMS is equal to now V peak, VR peak to peak. Just we have to write this expression in this. So IDC divided by 4√3 FC, where IDC is equal to what can we write? IDC is equal to VDC divided by RL. VDC divided by RL. So now if I write the expression VR RMS is equal to, what can I write? VDC divided by 4√3 FRC. So this is the expression for VR RMS. Now what we want? We want ripple factor. Now what is the formula for the ripple factor? Ripple factor is equal to VAC divided by VDC. So, and VAC RMS, we want VAC RMS value. So that is nothing but what? VR RMS. VR RMS is nothing but what? AC RMS value. VR RMS divided by VDC. Now in this expression, if I take this DC to this side, then I will get ripple factor is equal to VR RMS divided by VDC is equal to what I'm getting here? 1 divided by 4√3 FRC. Now if you see, this ripple factor is inversely proportional to the R and C values. By increasing the capacitor value, we can reduce the ripple factor. Or by increasing the resistor value also, we can reduce. Or by increasing both the values also, we can reduce the ripple factor. Now, this is the ripple factor derivation for in the case of capacitor filter.